Okay, so we can thank our next speaker, Anton Kapustin, and he's going to talk about symmetries, anomalies, and about boundary correspondence. Yes.
It's all the both mathematicians and physicists in the audience. Talk about something which is well, eventually related to categorical symmetries, but there's some more connection just with the higher symmetries. Let's make a case that probably understand the anomalies of ordinary symmetries. What we call them. One needs actually to involve higher symmetries, so this is this becomes apparent really only in starting with four space-time dimensions. So in two space-time dimensions, where like the first place where anomalies appear, really you don't need high-form symmetry, but also in higher dimensions, seems like you do, and maybe that's why our understanding of anomalies in two space-time dimensions is much better than in higher space-time dimensions. So, but let's start with making a little dictionary between. Well, I'll start with QFT, but then later move on to lattice models. So, physical notions. I want to motivate why I'm studying some particular well, in particular why I should think about lattice models. But let me just start. So let me close. So more physical objects. So it's slightly more physical part. This is slightly more mathematical part. For example, quotes in both directions. We have inside actually. So it's a unitary. E+1 space-time dimensions. So in here I'm gonna usually use denote D to denote spatial dimensions, so it's E+1. But if you want to have a sort of more physical notion, then something more related to like actual physics in a lab, then here's the gapped lattice models in D dimensions, which I mean some model of spins on a D-dimensional on D-dimensional lattice in D-dimensional Euclidean space. I'm not going to specify lattices, but you can also imagine just a hypercubic lattice. And gapped, I'm going to explain now. I'll explain later what this means, but some condition which ensures that it costs energy to create local excitations in the system. So, and the connection is that it's believed that from any unitary topological quantum field theory gives rise to some equivalence class of lattice models under some well-defined equivalence, which I might talk about later. Now, the opposite direction does not hold, and it's not true in general that you can recover TQFT from this. Physics like these dimensions of lattice. Yeah, these dimensional lattice. So lattice, you can just imagine just this. But you can also imagine just some bunch of points in Euclidean space without accumulation, and so that it sort of roughly uniformly fill the whole Euclidean set. That's fine too. So, well, to make the connection a bit sharper, one can restrict both sides, well, so here you can just put it like you can look at the invertible. TQFT. And here also can look at invertible lattice models, the dimensions. And here it's believed that connection is both ways. So can from every TQFT can construct some equivalence class of well, from any invertible TQFT can consider some invertible lattice model up to certain equivalence, and also supposedly every one of these gives rise to TQFT, and it's not that this is also not proved, but it's believed to be true, and there are no counterexamples. For example, nobody knows how to write any of both. So there's some lattice models. So there are no lattice models which seem to challenge this relation. Although for some invertible TQFT, there's still no lattice models we know how to construct. It's not clear sometimes how to do it.
Do you have a definition when a lattice model is invertible?
Yeah, that there's a definition, but this is a candidate definition. I'm not sure it's exactly right, but of course you need to tune definition so this works. So, but there is a candidate definition which physically reasonable, which just means basically that you can prepare your ground state of your model by starting with a trivial state where all your spins in the lattice are unentangled, just a product state, and prepare your state by unitary local evolution along with some junk which you just throw away. So you can evolve your unentangled state by some Hamiltonian for some finite time and get some state of a system tensored with some other junk. Okay, that's what it means to be invertible. This junk is really the inverse. So, and then one can throw in some symmetry in this business. We can add perhaps plus compensate. So some compact symmetry, compact linear symmetry on both sides, and suppose it also holds. Okay, so you look at invariant lattice models, G-invariant ones, also G-invariant TQFT or G-equivariant TQFTs. So now, so to make this more concrete, one can ask, okay, is there some way to check this? So let's say all these lines are kind of all these lines are conjectural. So what can one do? Make some checks. And the simplest check one can make is in the case with symmetry. And then because in that case, it's a further belief, but let's assume another thing is that for every invertible TQFT, you can assign anomaly in the dimensional QFT. So the physical picture here, why is that? Well, the physical picture is that if you have some TQFT in d+1 dimensions, then on general, it might not, on the boundary of this TQFT, it may not admit any topological boundary conditions. And then, so in that case, on the boundary, you must have some field theory. But that field theory, that field theory lives in one dimension lower with the D, and it's not uniquely defined by this guy, but supposedly, well, its symmetry is assumed to be the same because it don't assume without no symmetry breaking. You assume can all make some conditions without symmetry breaking. And then what is uniquely defined supposedly is the anomaly for this symmetry. So should be a way to assign it uniquely anomaly in one dimension lower to every invertible unitary TQFT in d+1 dimensions. And in fact, on the irrational level, I guess you could also do it even in this case. So there's if you neglect all the torsion phenomena. And say that G is a compact connector. The simplest examples of anomalies, historically the first one is the one where G is just a connected lead. So we're looking at the infinitesimals of anomalies, infinitesimal transformation. And this is the case where you really shouldn't be able to assign this anomaly even to just unitary GQ2, which is not necessarily invertible. So, and maybe therefore we can also do something similar for either this or that, invertible theories of for gap one. And then we have a sharp, yes, question?
How much does that adjective unitary matter for this connection to the anomaly?
Yeah, maybe it doesn't. But I just don't know in general what the anomalies are in non-unitary case. So, but people usually assume unitary as a physical assumption. So the good thing about this is that anomalies we can understand it much easier to describe than these things. And the anomalies we think we understand this on the rational level. And anomalies for this case is just element, some guy, well, classified by H D plus 2 classified space. Let's say with real coefficients. So that's what I think you can certainly assign uniquely to this guy. And we would like to assign something like this either to invertible lattice model or maybe to even to a gap lattice model. So someone has attach an element of that vector space to one of these two. And let me first describe it. Actually, now it's not. It's so how to do it was described in my paper with Nikita Sopenko. And let me the bulk of this talk is actually explaining how to do that. On just assigning some element from of this vector space. But then more specifically, we'd like to see something a bit more. We'd like to see that not just the same vector space, but the same elements in the same vector space are right, but actually they have the same meaning. That's a bit more complicated because actually we don't understand fully what this means even in field theory, except in dimension in dimension 2, so it equals 2. And I'll explain then how to work out this dimension 2, what this anomalies means, and they actually do mean the same thing. So how to extract, first of all, this element? So first of all, it's a lattice system. Well, first thing we need to do is to, well, we have choose the lattice. Doesn't know what it is actually. Some Dillon a subset, or D. Maybe just a hypercubic lattice, not that very important. Choose the C-star algebra. Which is going to be the algebra of all local observables. And we construct it standard. It's a very simple C-star algebra, it's called hyperfinite star algebra. You just take a product of some matrix algebras over all sites and take the closure. Because without that, it won't be C-star algebra. So this thing is really called the algebra of quasi-local observables, but I won't put any subscripts because there'll be another one. I don't want to have too many subscripts. So that's a basic object. But it turns out that to develop good theory, well, first of all, this is not going to get you anywhere by itself because this C-star algebra turns out doesn't care about the dimension of space. I never used nothing about the space I'm in. It's an infinite product. So each of these, for example, suppose each of these guys is just an algebra of 2 by 2 matrices, so the qubit. Take a product. It doesn't matter what this guy leaves here in R1 or 2 or whatever. Those get exactly the same C-star algebras. So you need some information. Well, if you want to ever discover that some group like this is irrelevant, then you need to put information about geometry or at least topology of this space. So that's incorporated by actually working with the better localized observables, something called almost local observables. So this guy, it's kind of like rigging. So in physics, well, mathematical physics, people often talk about not just say the proper arena for quantum mechanics is not just Hilbert space, which has very little information and they're all the same, but rigged Hilbert space. You put some dense subspace in a Hilbert space. For example, if you have, say, particle on a line, instead of taking like L2 function, you look at, say, smooth function which decay infinity faster than any power. So that's a similar idea. So here, the idea is to, well, and the point of this is that you want, the point of the rigging in the usual Hilbert space case, you want a good set of observables, which you can like multiply by or commute without any trouble. Say the momenta and coordinates seem like good set of observables, and you would like to at least take polynomial functions of those. If you work with this smaller Hilbert space, that looks well defined. So similarly here, we want some nice class of operations, say evolutions with some nice class of Hamiltonians to be well defined. To construct those, you need to pick something like that. And the specific that actually is, it's also a star algebra, but it doesn't have a C star structure, but it's an arranged thing, so it's called a fresh air star algebra. And then this does carry information about the metric on this space and therefore about topology. It's sort of like coarse topology of this space.
Is it hard to describe it more explicitly, like in terms of the lattice? Can you describe it more explicitly in terms of
I don't think we have the time for that, but roughly speaking, an element in the algebra of local observables without the completion is some just a finite product of matrices over some finite number of sites. Now, an element here can be thought of as a sum of such guys, where the norm decreases, so that the whole thing is, you know, the sum of norms is finite, right? Here, you want these approximations of the element here to by local observables be like very good if the radius of this of the ball which there is large. Basically, you want to be able to approximate any element here with the local observables and a ball radius r with accuracy which improves super polynomially as the radius goes large. Yeah. That's the idea. So
the dimension. So the dimension entered, for example, in
to the metric, to the fact that you have a metric, use metric on the balls. Yeah, so now the third ingredient here, most important one, is a state, which is a positive, just a positive linear function. That's also we're going to assume it's pure, you know, in some standard sense. So pure state. And that's so this setup avoids using Hilbert space, but once you have all these three things, well, the meaning of this is it's the ground state of the system. Given that, you can extract Hilbert space using the GNS construction and represent any element here by a bounded operator on the Hilbert space. But again, I avoid the Hilbert space as the plague because things get messy there. It's easier to work. It's actually almost everything can be done on the C-star level. So I'm gonna stay away from the Hilbert space. Well, maybe at the end of the talk, I will say something. Now, this state, of course, needs to be, not every state is acceptable. That's one thing which is kind of a new thing in this whole story, which is the notion of a gapped state. So, what does it mean? Well, so let me explain what this means. So first of all, we need some Hamiltonian, but I don't really care perhaps particularly what Hamiltonian it is. So the idea is that you're going to extract, so a system in principle, it's all this stuff, plus some notion of time evolution, such that this thing is the ground state for the Hamiltonian. But I'm going to postulate that there is some Hamiltonian which generates some time evolution, but I'm not going to, but none of the constructions depend on that Hamiltonian. It's really invariant. I'm going to construct some element in this vector space just given this data plus some property of psi. No further information is needed. What is this property? Well, there is a local, or almost local, Hamiltonian. Okay. Such that psi is with respect to it. H. So I need to explain what this means. So physically, Hamiltonian usually is just an unbounded operator in the Hilbert space. So, I'm staying away from the Hilbert space, so I cannot define it this way, but I can define, it's actually not convenient even to define the unbounded operator because it's kind of circular. I want to define, before defining Hilbert space, I need to find psi. But psi itself is a gap ground state of a Hamiltonian. So if Hamiltonian is a Hilbert space, it just makes no sense. So what H is, the derivation of this form of local observables. So that means that, well, it's a map from this algebra to itself, such that, now, well, it's derivation is true. Compatible with the star operation because it's well, I actually prefer to use anti-sulfide joint things, but so it commutes with the star operation. And then, okay, so and then what it means to be gap ground state? Well, that means the following: there is some number greater than 0 such that there's some bound on this thing. Well, it's some quantity which once you, if you translate it to Hilbert space, all this means is that in Hilbert space, you have a corresponding operator, unbounded operator, and you have operator also representing A. And what this means is simply this. That means that if you insert complete set of states here, that means that the energy of all state, which is not the vacuum, is actually greater or equal than delta. So that's how one can sort phrase being gapped with some non-zero gap in Hilbert space, but to understand the star algebra, we can just say it this way. And moreover, to proceed further, this H must somehow have a special form, which is actually standard in physics. So I'm going to say that so H is really defined like this: as an infinite sum, like this, where these guys are all Hj is also in this almost local observable. So an infinite sum. If we're a finite sum, we could just say, well, just take some all these little h's, and this is just inner derivation, just commutative with some element of the algebra itself. But it's an infinite sum, so I cannot do that. So therefore, H is only capital H is only derivation. So that's well, in physics, all typical Hamiltonians have this form. Moreover, one typically assumes that this Hj is local observable, sort of living on side J, on some pole of some radius. But it turns out that it's not flexible enough. You have to allow some sort of tails, this super polynomial tail. That's why it's almost local. Okay, so that's the setup. That's what the system is. And then one can sort of add symmetry. Well, by symmetry, I just mean, okay, so symmetry, it's going to be at an infinitesimal level. Okay, so first of all, what are symmetries? Symmetries of the state. So a symmetry, because let's say the state is symmetry G, if you have a given homomorphism from your abstract, say, group to the group of symmetries of your state, and all symmetries of the state. But Here I'm not going to work in infinitesimal levels. Just want to specify Lie algebra, infinitesimal symmetries of a state, and they say G symmetry of a state just a homomorphism abstract Lie algebra to that Lie algebra all symmetries. So what is that? It just say we have we call Lie algebra D because it's going to be any symmetry is a sort of the group infinitesimal should be a Lie algebra. So we're going to have some special derivations of my algebra of observables, kind of like Hamiltonian. After all, Hamiltonian is an example of a symmetry. So any symmetry is going to be some sort of derivation. So I'll call this symmetry of a state. Well, any symmetry is going to be leaving this vector space, which is going to be Lie algebra. So what is it? Well, it's going to be a map of the form, similar form. Where is this guy? An element like that, so approximately here, so the inner derivation of this algebra, so it's going to be infinite sum of commutators, and each of these guys is like a charge, if you wish, on a living on some particular side of the lattice. Yes.
Is localized near J, is that physically, that's just the fact that you have the interactions in your system to allow it to localize near J is just allowing for the fact that in general you need interactions and local interactions in your system to get to, like for HJ.
Well, typical examples of symmetries act side by side. So you have this QG is going to be literally one side observable, just living in another.
For HJ, which you were talking about earlier, you said it wasn't flexible enough to have it localized on the site.
No, usually to get an interesting system, you need to be in some neighborhood. I'm going to even do like allow some tails, which go all the way to infinity.
Having local interactions in the
And here, even though physical symmetries typically live on, each of these guys may be living on with just some particular factor, this AJ, this algebra observables on site. Again, it's convenient to allow you have tails, okay? You go all the way to infinity if you wish, but fast enough. Okay. Again, so
This notation, like that's a D upper side.
the upper side.
Defining that basically by.
I'm defining. So say it's there if it's a derivation of this form, and it should be what means that symmetry of sign means that first of all, I have this. The second. Like this. So in Hilbert space notation, it means the following thing. So in Hilbert space notation, have this. So you can attach an unbounded operator to your symmetry generator and bounded one to observable, and you must have that. This is what means like absence of spontaneous symmetry breaking. On the left, but you can express it again as the C-star algebra.
So this is a global transformation, right?
This is global symmetry. Now, these things from a Lie algebra, you can easily check. Just the commutator of these two things is well defined. So and then say, well, so psi has symmetry. For Lie algebra G, if we're given, we have a homomorphism. Look at Q from D to. Yes.
I want to have like projective actions of G, then I need to weaken this
On
concept.
site? Well, we're staying away from that. So I'm actually not 100% sure why, but all this work on symmetry protected topological phases becomes meaningless if you allow projective representation on site. So, I mean the following that, no, let's just stay away. it only makes sense. The whole notion really makes sense only for on-site actions. I'm going to discuss, since I'm not really focusing on on-site actions, we'll not discuss this. Okay, so my goal is still to define this element here. So how to extract an element in some D+2 dimensional cohomology group from all this stuff.
Do you require this homomorphism to give you the QJ as well, or
well, let's say that for me, symmetry, just homomorphism from some abstract. If I say a state has symmetry group, Lie group, a symmetry G, little g, if I am given homomorphism like that.
yeah, no, but in your formula, the QJs are defined out
Yeah, I'm
of
sorry.
elements. You want to specify the central elements or in this homomorphism or not?
I'm specifying these things.
Yes.
No, not this should have this form.
Yeah. Okay. You don't. Okay.
But how it's important, by the way.
You don't want to lift it to the.
Yeah. But how it's important, these guys
Yes.
are not uniquely defined by this.
Yes. Exactly. Yeah.
Yeah. So that's actually the next question. What's an ambiguity there? So this has an analog in field theory. In field theory, you write similarly a charge as an integral of. So to naive, very roughly, you can say that Q is infinite sum. Even though the sum doesn't make sense as an observable, but it makes sense as a derivation. So in field theory, you simply write your charge usually as integral of charge density for the whole space. I like to think about charge density as a d-form rather than a function because then I can integrate without any metric. So this is analogous. And of course, in field theory, it's well known that this charge density has ambiguities. You can add to it something exact, like with divergence, and then it doesn't change the charge. What the analog here also is it exists here too, but to define this, I need to introduce some natural algebraic gadget attached to lattice system. This is a natural complex. Sorry. Complex chains for a space, well, for a system. So, actually for a state.
I'm sorry if you answered this before. I would have maybe expected that the capital Q homomorphism mapped only from a central extension of G that up to some.
I don't think central extensions matter here because I work on the level of observables. I'll get back to central extensions. So maybe this will appear later anyway. But let me explain. First of all, central extensions in general are relevant only in some particular situations, in particular dimensions. So in one-dimensional field theory, quantum field theory, D equals 1. You can say that anomaly is central extension of the algebra observables. What does it mean? Well, the extension occurs not on the level of operator algebras, but on the level of operators in Hilbert space. That is, the point is following: that you have some Lie algebra of derivations, which does obey the usual accommodation. They're not central extension of your symmetry algebra. But then when you try to map your derivation to an actual operator, unbounded one, then it turns out that you're forced to get central extension. That happens only in dimension 1, d equals 1, that is space in dimension 2. So in higher dimensions, you don't have anomalies are not determined of central extension. That's the point that I'd like to actually clarify this, like to understand what happens in higher dimensions. That's the whole point of this in sense. But the point central extension occurs on the level of operator, unbounded operators in Hilbert space. Not on the, as far as derivations are concerned, you don't have central extension.
You have some higher.
Yeah, that's why in some sense, high cohomology classes are, it's not obvious why you should have why anomaly has nothing to do with high cohomology classes. Sort of a coincidence that central extension, simply coincidence that in 2 dimensions, 2 space-time dimensions, the same thing classify central extensions and the anomalies in some sense. But yeah, I'd like to understand this better. So, and actually, I'll sort of give you some hints how what actually happens in higher dimensions and why higher cohomology appears. And indeed, there is some sort of central extension appearing apparently, but it involves higher symmetries. But anyway, actually that's where sort of the first place where higher symmetries appear in some sense, because at this level, all you have is a Lie algebra of symmetries. But if you think about d-dimensional system, you think maybe some higher symmetries appear. So what's an analog of higher symmetry? Where are the higher symmetries? Well, maybe there is some, well, on the infinitesimal level, having a higher symmetry is basically the same as replacing your Lie algebra with some differential graded Lie algebra. So, so that is, there will be some complex. So there's some graded vector space with some Lie bracket, or maybe not quite Lie bracket, some homotopy Lie bracket, whose homology is actually that. That's a Lie algebra that itself. So, and physically it appears quite naturally once you start thinking about this chain complex, it appears quite naturally start thinking about ambiguities and defining these little q's. So, to define this chain complex is very important. So, so let's say that the one chain in this complex. Well, there's some funny business with shifting grading. You think that should be defining zero chains. Actually, in our paper, we define this to be a space of zero chain, but then I prefer to shift the brackets now because shift degree because I want to get bracket of degree 0, not of degree 1. So, so these are, well, so what is an object? Okay, let's move. What is this guy? Roughly speaking, the collection of almost local observables for every site of the lattice. So that's the density of a charge. So it's more complicated than that. If you just define it this way, it'll be no. I define everything so everything has a Fréchet structure. So I want to define complex of Fréchet vector spaces. So there's some fine print here, lots of it actually, which makes the Fréchet vector space.
A J. Last.
Oh, sorry, J. So, have this collection of observables, approximately localized on each site with some constraints. I'm not going to write them down to make things well defined. So this is like charge densities. So here we have a so what's a two chain? Well, the thing with two indices with the following property. First, it's symmetric, and second, local observable is localized simultaneously on I and J approximately. So, which means that, in particular, means that if you observe they are very far from each other, actually is 0, because the only thing which is localized on both is 0. So this object are symmetric basically and decay rapidly as I and J are far from each other, if you super polynomial. So what does this say? Let's look at physically, it's a current from I to J. Something flows from I to J. Naturally, when it flows from I to J, the opposite, we can also, because the negative of that flowing to J from J to I, that's a skew-symmetry condition. And similarly, of course, they have a, I call it different letters, so J is like a current, if you wish. Similarly, you get a collection of observables with 3 indices. And they're symmetric. And decay, well, you don't decay rapidly with the points. So physically, it's a bit less clear what this means. I put M because magnetizations are represented like this on the lattice. Anyways, and the build goes on and on. So, and then there is some we can think of this by two chains, either as ambiguities in the charge densities or as currents. So physically, either of them is the case. So, and for M, well, we can think of M's ambiguities in the currents. Because again, it's well known in physics that currents of a correspondence are actually ambiguous. And there are always improvement procedures for currents. And that's what this M is. It's a various improvements of currents which are compatible with conservation. And what else? What is the conservation equation? Well, on the continuum, it's exterior derivative. In the lattice, it will be summation over the index. So say wait, I forget. Okay, I should have put psi here. This is things that define just for lattice system without any psi. Where's psi here? Well, psi here, I want all these observables plus all observables to the first reserve psi. Meaning the same thing for it. So say what this. For other objects.
To just start, but you would call elements of AI local. Elements of AI for a specific AI, those are local.
Yeah, well, approximately local. Yeah.
Approximately.
You have tails. So this thing supposed to preserve, do not excite the state. It was the same condition as for this derivation here. Okay. You can also define similar thing with dropping this condition if you want. Then you get a different chain conflict, larger one, without this subscript psi. Anyway, and why it's complex? Well, we have this map which squares to 0, and it's just summation, say some object like the summation is well defined because all these objects decay rapidly when the point of. So okay, so that's a chain complex, and it's also easy to see that actually okay. So something which is one can actually make into a Lie algebra, differential grade Lie algebra. And what's the Lie algebra? What's the Lie bracket? The Lie brackets say of 2 0 chains. In an object one. Symmetrization. The commutator. So the brackets, maps, it's the right thing. It's a one. You start with a one chain. The brackets is a 2 chain, and so forth. So because the degrees works out fine. So the point is, so this is a different. So this is C psi delta bracket is a DG Lie algebra. Lie algebra. Now you can ask, well, why did they come up with it? Well, because, first of all, what is it? The claim is that some contributive theorem is that the homology of this thing is non-zero only in degree 0. And it's actually explicitly psi.
Sorry, don't you have that shift? I'm confused. It's like C0 is 0, wasn't it?
C1, sorry. Yeah, this. So yeah, because I keep forgetting that I shifted the grading since the paper was written. So have this result. So, and that's true if size gapped. I don't know what happens if size not gapped, but presumably this homologies are non-zero. And actually, I'd like to suggest that non-zero higher homologies have something to do with higher symmetries of the state. That if you have a gapless state, it has also might have also higher, like one form symmetries, two form symmetries, and so forth. And those have to do with higher homology of this in the algebra. And like I'm not going to have time to explain why, but that's the point. But for gapped systems, there are only zero form symmetries. That's what's this what it is. So well, you can if you wish, you can extend this complex by adding degree zero homology and then by adding this d sign, then you have no homology. So I actually prefer to work with this extended complex. So
Anton,
yes.
what happens if you refine the lattice? Do you study that at all?
I should refine lattice here, work for fixed lattice.
Yeah,
I don't really know how to put in this refine lattice here. So I've explained, at least in in D equals 2, how to extract an element of H4 of the symmetry. So so let me just say one more thing about this. So there's some map. So first of all, so if you have some, so in the continuum, we have four. The down over this chains of forms, like to integrate or somehow evaluate or something like that. So here, what do we do on the lattice? Well, this is sort of integration operation too. That's very important. Integration operator is really evaluation of a function at a point. So like analogous to continuum with a function at a point. So well, our one chains are d-forms, analogous to d-forms. But to get to a function, we need to sort of go up to integrating chain. So then I'll go over to see. So e plus 1 psi is analogous to functions on RD. And we'd like to sort of evaluation operation, and this is I'll call it so evaluation operation maps you from here the numbers, and I'll just write it down for d equals 2. Say t of say some m, say d equals 2. You take first of all, that's the local observable, it's going to evaluate expectation value, and then you sum, but you sum, of course, not over all values of I, j, and k. That first of all would sort of naively give you 0 because of skew symmetry, but non-naively would give infinity because you're infinitely many of these guys. They don't decay if you go far in space, right? So to get 0, you get infinity. Well, we're not going to sum something stupid like that. We're going to sum in a smart way. Or we're going to split our plane into sort of 3 sectors, don't have to be like this. We just need to choose orientation and sum like this. So that seems to depend on the choice of this point on this sector. It does depend on that. However, if it does not depend on A, B, C, if have this. Well, I mean that if you have the psi of m, just a bunch of numbers with the same properties, symmetric and decays rapidly. Then when I say this is true, that means the summation over any one index is 0. If that's the case, then actually this evaluation or integration doesn't depend on the choice of the sectors, only on orientation. Orientation just flips the sign. So this integration procedure, and now I can actually explain how to define, at least for d equals 2, the degree 4 class and homology. So remind you that H4 is the symmetric invariant symmetric polynomials on the Lie algebra of degree T. The quadratic function, basically. The G invariant. So how do I get one of these guys? Well, I do the following. So I start with this my homomorphism. So I have this Q. I use the fact that I have that my complex is exact, so they can also always write that to get little q and moreover, it turns out it's going to improve a little bit the statement. I can make sure that well, there's some improvements. So there's some technical property that I'm sure I'm going to talk about that. And then consider the following thing. Okay, so that consider Q with itself. Okay. It's a thing. Well, Q can think as a function of the Lie algebra. So because the bracket is the odd objects, so the bracket is actually symmetric. So this thing is symmetric object in the Lie algebra. It's a quadratic function of the Lie algebra, symmetric. With symmetric quadratic function. But moreover, that can be written as del of some right here, and the symmetric function on the Lie algebra. And then I can just apply to this T.
You're just doing descent. Yeah.
So, and then apply to this T. And this quadratic function in the Lie algebra. In fact, you can show it's invariant, G invariant. Okay, so that's my X. Okay, so far so good. So I just got what I wanted. I can extend it to higher dimensions. In higher dimensions, it turns out you get higher polynomials in the Lie algebra, higher polynomials. What I'd like really to see is that this is got some related to central extension of something. And what does it mean? Well, in a continuum, I can tell you what this means. Well, in a continuum, suppose this is just our Lie algebra U1. So Well, it typically says in that case, what does anomaly mean? Well, anomaly means that if you write your Q as an integral of some one form charge density, that's actually symmetry. Now, in field theory, it's sort of on the boundary of my two-dimensional system, really. These rows are, well, you can construct a row with a function. So, a real line or a circle, something like this. If it's a real line or a circle, it's a real line that happens to be like compactly supported. So I define this operators. Now it's not even clear they're well defined. The operators in Hilbert space. This is well defined in Hilbert space because of symmetry. These things are symmetries, sort of gauge symmetries. We call arbitrary function here. Gauge symmetries do not come into the Hamiltonian because we don't have a gauge field or anything like that yet. So this is not a symmetry. It's not unclear what can assign any operator to it in a Hilbert space. Turns out that for say for free permons, you can actually make some sort of fairly random choice and actually you can define an unbounded operator. But turns out that they don't satisfy the expected algebra. It would have to know these unbounded operators, turns out get some point here. The Schwinger term or central extension. So that's it took a cycle on the Lie algebra of functions, abelian Lie algebra of functions. So, by the way, this cycle kind of special. It's it's special in the sense only the only diffeomorphism invariant took a cycle. So how do I see this? Something is emerging from this construction. So it's actually very simple. The computation is the following. Suppose I the f g will be a function the functions on the lattice, which actually are which are smooth and depend only on the polar angle. That is, in this lattice, well, I have some lattice here. I pick some point which is not in the lattice. So for each point in the lattice, I have a well-defined polar angle. Okay. And then I evaluate this thing. Okay. And magically, it turns out actually this is QOM times the integral of f. So you could say, well, it was kind of predetermined that I get this expression. Well, I don't see why, because any skew-symmetric function of f and g would be a valid cocycle. I could put arbitrary, odd number of derivatives. It would still be well-defined cocycle. Nevertheless, I do get the right ones without imposing diffeomorphism invariance anywhere, just from this computation. So, that's why. So it's not just a formal correspondence. Indeed, this thing gives rise to the right cocycle. Now, similarly, I don't have the time, but if I went to higher dimensions, I would find. Let's just say what I could get. So, for the natural trivial case, d equals 4 actually, because in d equals 3, there are no anomalies infinitesimally. So it equals 4. And means on the boundary you have 4-dimensional QFT, 4 space-time dimensional QFT. In that case, Fourier cycles are not relevant. There's Fourier cycles. What do they measure? Well, in that case, turns out that well, this guy is somehow involves I already mentioned this higher chains are sort of higher form symmetries of the state. And as a result, here we have like a two-form symmetry. So if you think of this as a sort of attempt to gauge by saying that, well, this is a gauge transformation with parameter f, with parameter g. Try to gauge that, and we'll necessarily also need to gauge two-form symmetry. That's not a problem, provided there's no central extension. So now I can ask, okay, what is called M? And two-form symmetry takes two-form as a parameter. On a continuum with one of those dual objects, I'm going to dispel this out with some. But the point is that you get something like this. So I'll write the continuum version. So you get something like this. You get so your density and this is some two-form symmetry. And probably the two-form. So alpha is the four-dimensional space-time, space-time a three-dimensional space. And then now, but central extension is when you commute your zero forms and one form.
And sometimes a 2-form and sometimes a 3-form, or is it like 2 different things?
Well, maybe go down. So I distinguish lattice and continuum things. I call lattice things like little q and continuum on row.
Okay.
So maybe I should call continuum that. It's a continuum analog of this family. So from the continuum, you get also two-form symmetry, and extension appears in the commutator of the of your two-form symmetry and zero-form symmetry. So that's the point. So in general, to think about this takes values. This is a function of the Lie algebra. That's quadratic function in the Lie algebra. And if they compare it, this is actually going to be a cubic function of the Lie algebra. Yeah. So that's going to be messed up here. Okay. That's the cubic function. That's what classifies anomalies actually in 4 space-time dimension, cubic symmetric functions in the function on the Lie algebra. But the point is it appears as extension involving higher form symmetries. It's also cute.
So often we say that anomalies are classified as cohomological with
Yeah,
that's a related
level. Yeah.
Sorry?
I don't know how to extend this to the integral level. Plus, that statement about Z. So notice that I worked with general gap systems. So in the bulk, my TQFT was basically trivial, right? So in that case, anomaly is going to be sort of not quantized, right? In that setup. So I'm not working the fine enough level to see the difference between like invertible and gap. Invertible is the integral classes. I'm just working on fundamental levels. I don't see that.
Oh, I see. So if you look at sort of deformation classes, that might cut this down. And then you get some Z.
I'm saying that the setup I'm having, I have a QFT on the boundary, but on the bulk, I don't trivial TQFT. So this is called relative QFT. So as a result, my anomaly is actually not supposed to be integral in that setup. Unless typically people discuss anomalies, they think that bulk is essentially trivial TQFT, no anyons or anything, and then the anomaly comes out to be integral. But here I'm not assuming any of that, so I cannot refine it to an integral level. I need to refine to an integral level, actually I have to assume that my TQFT is invertible. I don't know how to do it in general, by the way. For dimension 4 in this case, when I can actually show that this is integral for invertible situations, but in general, I don't. For high dimensions.
The construction, you started with sort of a C-star algebra, but you weren't very specific about which one it was. So it feels like this
It doesn't matter, just any.
match is sort of universal thing, or
Any hyperfinite, no, I'm looking at this hyperfinite thing, so. So infinite product of a matrix algebras. It's not clear you can extend it to more general things like, in physics, sometimes we consider infinite dimensional on-site Hilbert spaces, sometimes it seems to be crucial. I don't know if this can be incorporated in this formalism because there are a lot of technical things under the rug. In particular, this theorem that the key theorem is this one. That you have no homology for this complex. And that I know how to prove only for have matrix algebras on site. So that those things depend on strongly on the what's called Lieb-Robinson bounds and this non generalization to infinite dimensional on-site Hilbert spaces.
There are no questions online. Can stop here. Thanks. No, you're perfectly clear. Yeah.
Or one of the schedule.